Semigroups and their representations, Lecture 12, Transitive Acts. So today we will talk about transitive acts, and for that let us start by reminding ourselves what an act over a semigroup is. So let S be a semigroup and X a set. So as we defined on the previous lecture, an action of S on X is just a homomorphism from S to the full transformation semigroup on X. That's an action by total transformations, by full transformations. If S acts on X, then X is said to be an S act. Similarly, an action by partial transformations, or a partial action of S on X, is a homomorphism from S to the semigroup PTX of all partial transformations of X. And if S acts on some set X partially, then we say that X is a partial S act. So homomorphism of S acts are maps between the underlying sets that intertwine the S action, and homomorphisms of partial acts are either partial or total maps between the underlying sets that intertwine the partial S actions. Now we can define transitive acts. So let S be a semigroup and X a partial and non-empty S act, or a total but non-empty S act. Definition: this act, or the partial act X, is called transitive, provided that for all elements U and V in X, there is an element A in S, such that applying A to U we get V. So from any element to any other element we can get by using the action of our semigroup. For example, a trivial act is transitive if and only if it is a singleton. So let's recall that a trivial act is an act where each element of the semigroup acts as the identity transformation. So if this act consists of one element, this is obviously transitive. If it consists of more than one element, this is not transitive. Example 2. The left regular act over a group is transitive. Indeed, if G is a group and U and V are two different elements in G, then applying the element VU inverse to U, we get V. So from any element of the group we can get to any other element of the group by left multiplication. Example 3. The natural act X over the full transformation semigroup TX is transitive. For any two elements in the set, there is a map from the set to this set, which maps the first element to the second element. And example 4, the natural partial act X over the partial transformation semigroup PTX is transitive. Next, let us talk about group actions on coset. So that's an example of transitive acts. So let G be a group and H a subgroup of G. Consider the set G modulo H, the set of all left cosets of H in G. So the elements of the sets are cosets AH, where A is an element in G. Then G acts on this set by left multiplication. An element B in G acts on the coset AH and gives the coset BAH. And, of course, the action axioms here follow directly from the associativity of the group operation. So we just multiply, and multiplication is associative. Let us note that this action is transitive, so the action of G on the set G modulo H is transitive, because for any elements A, B in G, applying BA inverse to the coset AH, we get the coset BH. So from any coset we can get to any other coset by left multiplication with some element in G. For example, if we take as H the trivial subgroup consisting just of the identity, then the set G modulo H is equal to G, and the left regular action of G on G is exactly the same thing as the action of G on the set G modulo H. Example 2. If we take as H the whole group G, then G modulo G is a singleton, and of course then G acts on this singleton trivially. Again, that's a transitive act which consists of one element. Now we can classify all transitive group actions. And a little bit note about terminology. When we speak about group actions, we always assume that the actions are unital, meaning that the identity element in the group acts as the identity transformation. So for groups, we consider only monoid actions. Theorem: let X be a transitive act over a group G. Then there is a subgroup H of G such that X is isomorphic as a G act to the action of G on the coset space G modulo H. Furthermore, for two subgroups H and H' of G, the corresponding G acts G modulo H and G modulo H' are isomorphic if and only if H and H' are conjugated in G. Proof: let X be a transitive G act and let U be an element in X. Consider the set of all elements A in G which stabilize U. So A applied to U is equal to U. So we consider the set of all such elements A in G, denote the set by H, and this is usually called the stabilizer of U, and denoted by stabilizer in G of U. Then we claim that H is a subgroup of G. Indeed, the identity element stabilizes U by definition, so it belongs to H. If two elements A and B belong to H, then AB applied to U is the same thing as A applied to the outcome of B applied to U, that's the axiom of the action. B applied to U is U because B stabilizes U, and then A applied to U is U because A stabilizes U. So we have just proved that AB stabilizes U. Also, if A belongs to H, then it stabilizes U, so A applied to U is equal to U. And now applying A inverse, we get that A inverse applied to U is the same thing as A inverse applied to A applied to U. Using the action axiom, we get A inverse A applied to U. A inverse A is the identity, so that's the identity applied to U, and this is equal to U. And so this means that A inverse also belongs to H. So H has the identity and is closed with respect to multiplication and taking inverses. So this is really a subgroup of G. Now we can consider the map F from G modulo H to X, which is defined on a coset AH in the following way. So F applied to AH is equal to A acted upon U. So the map F is well defined because A acted on U is equal to B acted on U if and only if applying A inverse to A applied to U is equal to A inverse applied to B applied to U, if and only if U is equal to A inverse B U, and this means that A inverse B belongs to H. And A inverse B belongs to H if and only if AH is equal to BH. So this shows that our action is well defined. Next, it is surjective because X is transitive. And this map is injective by exactly the same computation which we just did. A applied to U is equal to B applied to U if and only if AH is equal to BH. And this means that F is bijective. And also the map F is a homomorphism of G acts. Indeed, if we apply F to A acting on BH, this is equal to F applied to ABH, and this is equal to the application of AB to the element U. On the other hand, if we apply A to F of BH, that's applying A to B applied to U, and by the axiom of an act, this is equal to AB applied to U. So we have that F of A applied to BH is equal to A applied to F of BH. And so F is a homomorphism of acts. And then it's bijective and is a homomorphism of acts, so it's an isomorphism of G acts, and this proves the first claim of our theorem. To prove the second claim of our theorem, let us assume that H and H' are subgroups of G such that H' is conjugated to H. So H' is equal to C, H C inverse for some C in G. Then we can rewrite it as CH is equal to H prime C, and hence H prime coincides with the stabilizer of the element CH of the transitive G act G modulo H. And from the first claim of our theorem, we thus deduce that the G act G modulo H prime is isomorphic to the G act G modulo H. Now we need to prove the converse statement, so let us assume that G modulo H is isomorphic to G modulo H prime via some G act isomorphism which we denote by F. Let us note that the G stabilizer of the element H in G modulo H is equal to H, and since F is an isomorphism, it means that the G stabilizer of F of H, and that's some coset A times H prime, and that's an element of G modulo H prime, the G stabilizer of that element must be equal to H. But we have that B applied to AH prime is equal to AH prime if and only if A inverse BA belongs to H prime. But this means that the G stabilizer of this element AH prime in G modulo H prime is actually A H prime A inverse, so that's a conjugate of H prime. And from this we deduce that H is equal to A H prime A inverse, and so H and H prime are indeed conjugated in G. And this completes the proof. Now let's discuss the connection between transitivity and invariant subsets. Small remark, if not explicitly stated otherwise, when we say act, we always mean a non-empty act. Proposition: an act X over a semigroup S is transitive if and only if the only invariant subsets of X are X and the empty set. Proof: assume that X is transitive and that Y is a non-empty proper subset of X. Take some element U in Y and some element V in X minus Y. Then, due to transitivity, there is an element A in X such that A of U is equal to V. But then Y cannot be invariant. So any proper non-empty subset is not invariant. So that proves one direction of the proposition. Conversely, assume that X is not transitive and that U and V in X are two elements such that we cannot come from U to V by applying any element A in S. So A applied to U is not equal to V for any element A in S. Consider the set Y, which is defined as A applied to U, where A goes through all elements in S. That's definitely different from the empty set, and it's different from X because it doesn't contain V. And this set is invariant because if we apply B to A applied to U by the act axioms, this is equal to BA applied to U. So we have now an invariant subset which is different from the empty set and X. And this completes the proof of the proposition. Now we can describe the relation of transitivity to minimal ideals of semigroups. Proposition: let X be a transitive act over some semigroup S, and let us assume that S has a minimal with respect to inclusion left ideal I. Then X is a transitive act as an I act. Proof: to start with, let us note that any ideal is a semigroup itself, so it makes sense to speak about acts over this semigroup I. So if X is not transitive as an I act, by the previous proposition there is an I invariant subset Y in X, which is different from the empty set and from X. Let us denote by Z the set of all element A applied to U, where A is an element in I and U is an element in Y. Then of course Z is non-empty, and it belongs to Y, which means that it's different from X. For an element B in S and an element A applied to U in Z, so Z consists of such elements, we have that B applied to A applied to U is equal to BA applied to U, But here B is an element in the semigroup and A is an element in a left ideal. So BA is an element in the left ideal, so our BA applied to U belongs to Z. So this means that our set Z is S invariant. Now as S-act, it's an invariant subset as an S-act. But then this contradicts the previous proposition, because we have found a non-empty proper subset which is S-invariant, so our original act cannot be transitive. This has the following consequence. Let S be a semigroup with 0, then, corollary, any transitive S-act is isomorphic to a trivial singleton act. Proof. Clearly, the subset of S which contains of the 0 element is a minimal left ideal of S, and so by the previous proposition, if X is a transitive S-act, it must be transitive as an act over the 0. The element 0 acts as an idempotent transformation of X, and any element in the image of this idempotent is invariant under this idempotent. And so X must coincide, due to transitivity, with this element in the image, so it must be singleton. So we have now described all transitive acts over semigroups with a 0 element. Next, let us classify all transitive acts over the full transformation semigroup Tn. Theorem: let X be a transitive act over Tn where n is a positive integer. Then X is either a trivial singleton act or is isomorphic to the natural Tn act, so that's Tn acts on the set 1, 2, 3 and so on all the way up to n, and we denote that set by n underlined. Proof. The semigroup Tn is finite and has a minimal left ideal. And in fact, that minimal left ideal I is unique and it consists of all transformations of rank 1. So let's denote those transformations by special symbols. So for an element A in n underlined, we have the transformation pi A, which sends all elements in n underlined to A. So that's a rank 1 transformation. Let us note that each pi A is a left 0 element of the semigroup, which means that pi A after any sigma from Tn is equal to pi A. And also note that our minimal left ideal I is in fact a two-sided ideal, so all rank 1 transformations form a two-sided ideal. So let X be a transitive Tn act. For an element A in n underlined, let U sub A be an element in X, which is some element in the image of pi A acted on X. And let Y be the set of all elements V in X, such that pi A applied to V is equal to our UA. So that's UA. Then UA belongs to Y, so Y is a non-empty set. And also, if sigma is an element in Tn and V is an element in Y, then U, that's our UA, is equal to pi A times V, and this is equal to pi A after sigma times V because pi A is a left 0, and this is equal to pi A applied to sigma applied to V. And this means that sigma applied to an element in Y belongs to Y, so Y is Tn invariant. So now, due to transitivity, Y must be equal to X, and in particular pi A is a rank 1 transformation of X. It sends all elements of X to our element UA. So pi A acts on X as pi UA. So now we define Z as the union of all those UAs where A is an element in n underlined. And that's of course a non-empty subset of X. If we take an element sigma in Tn, we have that sigma applied to UA is equal to sigma applied to pi A of UA. This is equal to sigma after pi A applied to UA. Sigma after pi A is of course pi of sigma of A applied to UA, and this is equal to U sigma of A. And this proves that our Z is Tn invariant, and so it coincides with the whole of X due to transitivity. Let us first assume that all UA are different. Then, sending an element A to UA is bijective, and by the computation above, a homomorphism of acts. So this computation means that sending A to UA is a homomorphism of X. So this is an isomorphism from the natural Tn act and underlined to X. Next, let us assume that there are two elements A and B which are different, but such that UA is equal to UB. So A and B are elements in N underlined. Let C and D be two arbitrary different elements in N underlined. Let sigma in Tn be some element which sends A to C and B to D. This obviously exists. But then sigma after pi A is equal to pi C, and sigma after pi B is equal to pi D. Since pi A and pi B act on X by the same transformation, applying sigma we obtain that pi C and pi D act on X by the same transformation. In other words, all URs which we have coincide, so not only UA and UB, but all URs coincide, and so X is a singleton. And this means that X is a trivial singleton act. And this completes the proof of the theorem. Next, let us describe transitive acts over rectangular bands. Let's recall what a rectangular band is. Let A and B be two non-empty sets, and from these two sets we can construct a semigroup which is called rectangular band as follows. As a set, S is equal to A times B. And the semigroup operation is defined as follows. If we multiply the pair x, y with the pair u, v, we get the pair x, v for any x, y and u, v in A times B. So all elements in this semigroup are idempotent. In particular, that's a regular semigroup. It has a unique J class, so it's the same thing as a D class in this case. And the left classes are in bijection with elements of B, and if we fix D in B, the corresponding left class, which we denote by LD, consists of all pairs x, d, where x is in A. And similarly, right classes are in bijection with A, and have the form RC, where C is an element in A, consisting of all pairs C, y, where y is an element in B. So let ρ be an equivalence relation on A. Consider the set of all equivalence classes, A modulo ρ. As usual, for an element C in A, we denote by C overline the ρ equivalence class containing the element C. Lemma: for x, y in S and C in A, setting that x, y acts on C overlined to give X overlined defines on A modulo ρ the structure of an S act. Proof: let's take two elements x, y and u, v in S, and let C be an element of A. So acting by x, y on u, v acted upon C overlined, we get x, y acting on. So u, v applied to C overlined is u overlined by definition, and if we apply x, y to u overlined, we get x overlined. On the other hand, x, y times u, v is equal to x, v. So if we act by x, v on C overlined, we get x overlined. So we see that we have the same thing, so the axiom is satisfied, and this proves our lemma. Now we can classify all transitive acts over rectangular bands. Theorem: any transitive S act X is isomorphic to A modulo ρ for some equivalence relation ρ. Moreover, A modulo ρ is isomorphic as an S act to A modulo ρ prime if and only if ρ is equal to ρ prime. Proof: let X be a transitive S act. For an element C in A, the set LC is a minimal left ideal of S. Hence X is also transitive as an act over this minimal left ideal LC. Note that every element in LC is a left zero in LC. It's not a left zero in S, but it is a left zero in LC. And so we can use exactly the same argument as in the classification of transitive Tn acts, and get that each element of LC must act as rank 1 transformation of X. Also, the union of the images of all these rank 1 transformations is the whole of X. Now we can define the relation ρ, that's an equivalence relation on A, as follows. For uv in A, u, v belongs to ρ if and only if uc and vc act by the same transformation of X. And now it is easy to check that sending for u in A the class u overlined with respect to ρ to the image of u, c is a bijective homomorphism of S acts from A modulo ρ to X. And this proves the first part of the theorem. And for the second part, we know that the kernel of the action map from S to the full transformation semigroup on A modulo ρ can be described as follows. X, y and u, v act as the same transformation of A modulo ρ if and only if x, u belongs to ρ. And this directly applies that any isomorphism between A modulo ρ and A modulo ρ prime yields that ρ is equal to ρ prime. And this completes the proof. And finally, let us talk about transitive acts over the additive semigroup of all positive integers. Proposition: let X be a transitive act over the additive semigroup S of all positive integers. Then X is finite, and the element 1 in S acts on this finite set X as a cyclic permutation of the elements of X. Proof: take some u in X and consider the set k applied to u, where k is a positive integer greater than 1. This set is obviously S-invariant and non-empty, and so it must coincide with X. In particular, it must contain the element u. But then this means that there is an element k which is greater than 1, such that k applied to u is equal to u. Consequently, 1 acts as a cyclic permutation of the elements u, 1 applied to u, 2 applied to u, and all the way up to k minus 1 applied to u, where k greater than 1 is the minimal possible element such that k applied to u is equal to u. Additional problems and questions at the end. Problem question 1. In the proof of the theorem on transitive actions of groups, prove with all details that H' coincides with a stabilizer of the element CH of the transitive G act G modulo H. Problem question 2. Prove that any finite act over a finite semigroup with 0 has a fixed point. Problem question 3. What can one say about a semigroup S if we know that the left regular S act is transitive? Problem question 4. What can one say about a monoid M if we know that the left regular M act is transitive? Problem question 5. Fill in all the details in the classification theorem for transitive acts over rectangular bands. Thank you very much, and see you next time.